In this video, I will discuss the use of pKa values in determining the directions of an acid and base reaction. So again, in an acid and base reaction, two substances are competing to bond to the proton, and the proton will then be bonded or will go to the substance that one is more, and that the substance with a higher pKa for that proton. So when using pKa value, our emphasis is on the acid and the conjugate acid. And we asking ourselves, which of those substances has a higher pKa? And equilibrium will then be favored to the side that have the higher pKa value. Now, when we use ARIELs, our emphasis is on the base and the conjugate base. But when we use a pKa value, we can now emphasize on the acid and the conjugate acid. So in this reaction right here, as an example, this is our acid. Once this acid had given up this proton already, the rest of this will then become the conjugate base. And once the base has picked up the proton, what is become would now be the conjugate acid. And now by comparing the pKa of this acid and this conjugate acid, we can then determine the directions of equilibrium in this reaction. So let's call this pKa value right here. This is pKa, meaning the pKa of the acid. And this pKa value right here, let's call this pKa, Ca, or the conjugate acid. So if the pKa of A of the acid is then equal to the pKa of the conjugate acid, meaning the two substances has equal affinity to bind to the proton, or they both want the proton equally, then we will then see that both of them will have equal chance of binding to the proton. And that's why the concentration of the acid, both of them will get produced, and the concentration of the acid is then equal to the concentration of the conjugate acid. So yes, there will be a reaction, but we'll be having distributions or concentration between the acid and the conjugate acid will then be equal. Versus if the pKa of the acid is much lower than the pKa of the conjugate acid. So that means the conjugate acid want this proton more, and if they want it more, it will then favor the product side. So the product side will be favored when the pKa of the conjugate acid is much higher than the pKa of the acid. And oppositely, if the pKa of the acid is much higher than the pKa of the conjugate acid, this is when the reactant side will be favored. And that basically means there will be no reaction. We do not proceed to the product side. And here's something very important to take notice right here. For every x pKa value different between the acid and the conjugate acid, so let x represent the differences in the pKa value. Then for every unit of pKa value that is different, the equilibrium concentration is then shifted to the side with a higher pKa value by a factor of 10x. So if one pKa value is 1 unit higher than the other pKa value, that basically means that it exists in 10 times more compared to the other substance. For an example, let's say here in this case right here, we have this reaction, take an acetic acid and reacting with hydroxide. And here in this case, this is our acid and this is our base. And this would then, hydroxide will come in, grab the proton from acetic acid, and the electron will then give into acid to the oxygen, forming acetate. And as for hydroxide, this will now become water. So we're going to see that this is the acid, and we need to determine the pK. In this case, the pKa of acetic acid is 4.75. And now, after the base had picked up this proton already, it becomes water. And this is our conjugate acid. And the pK of this equal to 15.7. And now when we compare the pK of the acid and the conjugate acid, there is a huge difference between the pK value. In this case right here, this pK value right here, if we take 15.7 minus 4.75, this would then equal to 10.95. So the concentration of the product side would be favor much more than the reactant side. And in fact, it will equal to the following. It will be 10 to the 10.95 times more. So once this reaction has reached equilibrium already, the concentration of the product will then be this much time more than the concentration of the reactant. So we would then see reaction would then be pushed to the product side heavily. So that's how we can use pKa's to quantitatively describe the equilibriums of an acid and base reaction. And now let's try another example. So here is the reaction right here. Acetone, a reactant with hydrogen ion to produce this two product right here. So in this case right here, this is the base and this is the acid. And once this base has picked up the proton from the acid, it's now become the conjugate acid. And this will then become the conjugate base. And again, we need to compare this pKa and this pKa. So the pKa of the acid in this case right here for hydrogen ion, this is equal to negative 1.74. And the pK of this, using the value from the previous pK table, is equal to negative 7.3. So we will then see in the course of this reaction right here, this is the side with a higher pK value. So negative 1.74 is much greater than negative 7.5. So in fact, so therefore we can see that once this reaction have reached equilibrium, most of the substance that exists will then be the reactant. So this would be 10 times to the 5.56, 10 to the 5.56 times more in terms of the concentration compared to the products. So we will then see in this case right here that the reaction is favoring the reactant side heavily. So therefore there will be no reaction. So that's how we can use pK value to determine the directions of equilibrium of an acid and base reaction. And if the product size is in favor a little bit over the reactant side, we will consider that to be a reaction. Versus if equilibrium favor the reactant side slightly more, then we will then consider that to be no reaction. And this would be the guidelines to determining acid and base reaction. So to determine whether an acid and base reaction would occur or not, these are the steps or guidelines that we can follow. First, identify the most acidic proton in the reactants they given to us. And the substance having the most acidic proton on it would then be the acid. And again, we can basically look up pK value to identify the most acidic proton. And after we have identified the most acidic proton already and its pK value, we ask ourselves this next following question. Can this acidic proton right here be transferred to another substance to produce a substance with a higher pK value? So can we transfer the proton to another substance, and that substance would then be a base right there to produce something with a higher pK value? And if the answer to this is yes, we can transfer this to another substance with a higher pKa value, meaning there will be another substance that want the proton more. So therefore, the substance that want the proton more will go ahead and grab the protons from the previous substance, causing a chemical reaction to take place. Versus if the answer is no, we cannot transfer the proton to another substance with a higher pKa value, then there will be no reaction. So that's how we can use pKa to determine whether or not an acid and base reaction would happen or not. And alternatively, we can also use ARIEL to evaluate the stability of the base and the conjugate base. So first assume a reaction going to take place. What would be the base and the conjugate base? And draw the structure of those two substances. And then use ARIEL to qualitatively compare the stability of the base and the conjugate base. If the conjugate base is more stable based on ARIEL analysis, then acid and base reaction will occur. So these are the two methods that we can use to determine whether or not an acid and base reaction will happen, by either using pKa or use ARIEL and compare the stability of the base and conjugate base. So please try this following example. And perhaps maybe let's work on one. So in this first case right here, when we take HCl reacting with water, then follow our guideline over here. First, identify the most acidic proton in both of this molecule. HCl's have that hydrogen with a pK equal to -7, versus for water, it has one hydrogen with a pK of 15.7. So we will then see that this is the most acidic proton right here, and that makes this the acid. And the other substance will then have to be a base. So in the course of this acid and base reaction right here, the base will then come in and grab the proton from the HCl, give an electron to this chloride right here, and we will have H3O plus, and the rest of this will then be the chloride, the negative. So that will be the product right here. And this is our conjugate acid, and this is our conjugate base. And now if we were to, so let's first try using ARIEL to determine whether this reaction would proceed or not. When we use ARIEL, we'll be comparing the stability of the base and the conjugate base. And this, here they are. So in this case right here, we have water and chloride. Which of this would be more stable? And in this case right here, this is actually not easy for us to determine which one is more stable, because we are comparing different types of element, and they also have different charges on them as well. So this is where it gets a little bit tricky and difficult for us to use ARIEL to determine the stability between these two substances, since they're not apple to apple, because one of them is neutral and the other one is negative, and they have different atom on them, so quite difficult. And in fact, that would be the limitation of ARIEL. But now let's see if we can use pKa to determine this reaction right here. And whenever we use pKa, we now need to be looking at the acid and the conjugate acid and compare the pKa. So here it would be. So this pKa right here is -7, and the pKa of hydronium ion, so this will be -1.74, versus this is pKa of -7. So we will then see that the product side has a higher pKa. So meaning water wants the proton more, because when it have the proton, this is how much potential that it has for the proton, which is much higher than HCl. So therefore, equilibrium will be favoring the product side. So this is a good example to demonstrate that pKa is basically a more powerful tool compared to ARIEL, because it provides quantitative assessment. Please try the other example.